record now. And let's all welcome Matthew, and let's all get ready to learn about organometallic chemistry in action.
Right, and before you you mute yourself, Lauren, I think Carly has a question about when the coding class is.
Muted. So Carly, are you talking about the GIS class?
No, the last one of these I did, they were talking about doing a coding class, like with computers, and we went online to look for it and it wasn't on there. So I was wondering if you knew anything about it.
I do. So the coding class is called 4-H World Changers. And we're actually in week 5 of 6 weeks right now, where we're learning Scratch. But we have another session coming up that's going to start right at the beginning of February, where it's going to focus on Python.
Okay, thank you.
You're welcome.
Ooh, Python. All right, well, let's go ahead and get started. So first and foremost, let me thank you all for attending today's Teen Science Cafe. I'm really excited for everybody in this session to learn about my research, which relates to heterodehydrocoupling and how, that can be utilized to efficiently produce silicon nitride nitrogen bonds. And so a few things.
Now get in here now.
A few things to note is that you may call me Matt or Matthew. It doesn't matter to me. You don't need to call me Mister. I'm not that old, and you don't need to call me doctor because I don't hold a PhD in chemistry. And so feel absolutely free to, interrupt me while I'm talking. You may, just put a question in the chat, and I will try my absolute hardest to get to it if you do have a question that needs to be answered. And I'm really hoping that this presentation will be, a bit of an informal process rather than, just a 50 minute long lecture that you just have to sit through. Believe me, I've been through many of those myself. I know every single one of you in this chat right now is probably experiencing that nightmare. So hopefully we can, get this to be a bit of a little bit more engaging process. And there we go. And so over the course of the next 35 to 40 minutes, I hope to relay to you, the linear story that is, me starting in my academic, career in high school, undergrad, and grad school, and how that relates to how I got into organometallic chemistry and my research in total. And, we'll be discussing a few other topics along the way, such as, general chemistry, synthetic chemistry, stoichiometric chemistry, and how that can segue into catalysis and the overall topic of this conversation, which is heterodehydrocoupling. And, that will take, half of the presentation. And after that, we will probably close on my own research, which will be related to iron catalysis and the potential of lanthanum in catalysis. And I recognize that most of you probably don't understand a lot of the topics that I just went over there, and that's perfectly okay. But if there is one key talking point that I want everybody in this chat to really take away from this presentation, it's that dehydrocoupling is a green, efficient pathway to forming chemical bonds through catalysis. Say that over and over again, inside your head. Say it as many times as you need to actually, retain it and remember it throughout this presentation. It's perfectly fine if you don't understand it now. Hopefully by the end of this presentation, you will. And so just a little bit about me. I'm Matt. I'm a 4th year grad student at the University of Vermont's chemistry department. I was born, raised, and primarily educated in New Hampshire. And a few fun facts about me is that I'm a big fan of Naruto, Star Trek. I love pizza and hiking. I have not had as much time to hike in grad school, unfortunately, but I'm really hoping that I can, get back into it. But a little bit more interesting about me is that I have 3 cats, 3 beautiful kitties, Athena, Loki, and Tilly. Fun fact, about an hour ago, my wife saw this picture and she saw that she was not in it and she was very upset. So I have some explaining to do later on today. But I guess the story really begins about a decade ago, where I received my, education from Merrimack High School between 2010 and 2014. I got a diploma in core curriculum. I had 1 class in chemistry, and I didn't really find my love of, the field, at that point in time. And it really wasn't until I made my way about, an hour away from my hometown at the University of New Hampshire's Durham campus. And, I guess a bit of a sidetrack is that if there are people in your life telling you that you really need to, find the direction you need to go to before you go into college, I didn't find what I wanted to do, in college until my sophomore year. And I didn't really find my love of chemistry until the senior year. So if anybody's telling you that, that's complete BS. But after that, in 2018, I immediately enrolled in the graduate program at the University of Vermont, where I am working towards my PhD in chemistry. And I'm doing my thesis work on catalysis and catalytic development. And this is being conducted under the tutelage of Professor Dr. Rory Waterman. Rory has an absolutely laundry list of awards, so I'm not going to bother going into that. He is, an incredibly intelligent person, and he has connections all throughout the world. So, he is a big name in organometallic chemistry, and, I'm frankly lucky to work under him. But this is the group about 2 years ago. This was pre-COVID, so unfortunately we have not had time to, update our group photo, but hopefully we can do that soon. And so, this really segues into, what the group does, which is organometallic chemistry. But, something that's really fundamentally important about our work is that from the title of this slide, our compounds really don't like to exist under ambient conditions. And, at the end of the day, what we try to accomplish can be minimized with the following statement. We like to make stuff. We like to make stuff that is potentially important to both academia and industry, and we like to make that from commercially available reagents such as silanes and phosphines. Silanes are small molecules that have a silicon hydrogen bond, and phosphines are small molecules with a phosphorus hydrogen bond. Actually, let me just change over my pointer. There we go. And what's really important to take away from these compounds is that they don't like to exist under ambient conditions. In the case of silanes, they readily react with water to liberate hydrogen gas and form strong SiO bonds. Phosphines, on the other hand, readily react with atmospheric oxygen to form phosphine oxides. And, these products might have inherent, utility to other groups, but they really don't serve our group, much purpose. But what's more important to take away from this is that under normal laboratory conditions, such as a benchtop or a normal fume hood that some of you might have seen in a chemistry course, these compounds will readily ignite and potentially explode. And, it makes it extremely difficult to work with it under ambient conditions. And, another side note, despite my best urgings, my boss informed me that replicating this for educational purposes was not a good idea. So unfortunately, you will have to use your imagination on what that disaster would look like. But how do we overcome this as, trying to work with these silanes and phosphines in, an agreeable manner? Well, we employ two specific techniques to get around this issue. We utilize something that's called a Glovebox and something that's called the Swingline. And in their simplest forms, they accomplish the same goal. They try to exclude atmospheric oxygen and moisture from these sensitive compounds. In the case of a Glovebox, there is a physical barrier between the inside atmosphere, which is composed of nitrogen. This is unreactive towards these compounds, and it essentially keeps out atmospheric oxygen and moisture, allowing for the manipulation of small-scale reactions as well as the storage of these chemicals indefinitely. A Swingline works in a similar fashion where it is able to alternate between a vacuum and a nitrogen atmosphere. And essentially how this vacuum works is that it's able to basically suck out any moisture and oxygen from a reaction and refill that with a nitrogen atmosphere. And this is actually a lot of where our synthetic techniques come from. This is where we're able to make a variety of our compounds. And unfortunately, a recurring trend you will see in this presentation is the poor quality of these photos. That was taken from my camera, and unfortunately, there's nothing I can do about it. So I'm very sorry about that. So we're actually going to segue we're actually going to take a step back and talk about some of the chemical steps that are necessary to understand this research. But I was just wondering if anybody has any questions thus far, because we will be taking a sideline into what we want to accomplish. That's a great question, Gabby. So Gabby's question is, what does organometallic mean essentially? And that's actually going to be discussed, I think in the next slide. But essentially what organometallic means is that it's combining two sections of chemistry, organic chemistry and inorganic chemistry, specifically the part of inorganic chemistry that is composed of metals. So organometallic chemistry essentially means that there is a metal carbon bond being used in this catalysis. And Oren also has another excellent question. What are silicon bonds used for? And that's actually going to come up later in the talk, so I'm not going to get to it quite yet, but we will touch upon that in a few slides down the road. But yeah, any other last minute questions? I just want to make sure that everybody's kept up to speed and is actually learning something. Okay, so let's just take a step back from some of these techniques that I've actually discussed and just go back to chemistry in general. What is what is chemistry? I think this is the first question that I would like to pose to some of you. I don't know how interactive this section is going to be, but I would just like to ask everybody, what does chemistry mean to you? That can just mean what it might be taught as in high school, or what you have come to understand it. What does chemistry mean to you? I'd like to take 30 seconds and just write in the chat, what is chemistry? All right. How atoms and molecules interact. Yeah, that's a great one. Yeah, so chemistry is, so Brianna, chemistry is the study of atoms and how they interact with one another. Gabby, it involves elements. Like all of these, these are correct in the subject that you fail in every test. I definitely have in the past. Yeah. So, this is great feedback. I'm really enjoying the fact that everybody is being engaged in this process, but, everybody is right in the sense that chemistry is really the study of matter and how that matter can change. But one thing that is commonly encountered, in this definition, especially in high school and undergrad, is that this field is more often than not just squeezed together and combined. And in reality, chemistry is really the culmination of four main groups. It is analytical chemistry, which is the quantification of chemical substances. There's organic chemistry, which is the study of substances and transformations with carbon. There's inorganic chemistry, which is the opposite of that. It's substances and transformations without carbon. And there's physical chemistry, which is the study of thermodynamics and kinetics of chemical systems. And this really touches upon, an issue that is really taught with chemistry at both high school and undergrad level. It has a tendency to just, skim over what is really important and what really divides these chemical classes. But these fields can be further subdivided into more specific professions, as well as more specific careers, such as computational chemistry, organometallic chemistry, biochemistry, and chemical engineering. And as I just discussed a few minutes ago, organometallic chemistry is the culmination between organic chemistry and a subsection of inorganic chemistry that deals with metals and organometallic compounds. So Aaron has a question. Why does carbon separate organic chemistry and inorganic chemistry? Can't carbon be in a non-organic context? That's a great question. And I guess this is really a question for, the people who actually discovered the field. They're the main reasons why these two things separate. At the end of the day, there are a lot of fundamental transformations that have been done with carbon. It was actually, I think, the start of the synthetic field back in the 1880s, I think it was. So there's a lot more, emphasis on organic chemistry, which just so happens to incorporate a variety of carbon atoms. And I think it took 60 to 70 years for inorganic chemistry to really spring from that root. So, there's a variety of answers to that. I don't think I can really, I don't think I can really give a good answer without giving you a good course on that. But from here, we need to, kind of segue into what synthetic chemistry is. And in essence, synthetic chemistry is just our way of taking some sort of reagents, A plus B, reacting them under certain conditions to form a certain product and another byproduct. And this can be, a variety of substances. In the case of trying to make a silicon-nitrogen bond, we can take some sort of amine, in this case, ammonia. Amine is something that retains a nitrogen-hydrogen bond with a, silicon fluoride bond to form our silicon-nitrogen bonds and a byproduct such as hydrogen fluoride. Another stoichiometric reaction that we can potentially do is react in water with that same silicon fluoride bond to form polymeric SiO bonds. And just to hit upon this last product a little bit further is that these silicon oxygen bonds are very often, they're ubiquitous in everyday life. They are commonly encountered due to their low chemical reactivity, their high temperature stability, and their overall low toxicity. They're frequently utilized in sealants. And I utilize this example in particular because this really touches upon what the Waterman tries to accomplish, the Waterman group tries to accomplish, or at least half of that. We try to make p-block bonds and products that may be academically and commercially relevant and may have some sort of inherent chemical or physical properties. But, an issue starts to arise from this type of synthetic chemistry, and that's the formation of stoichiometric waste. So going back to our previous examples where we have some sort of products such as C and D, our D product is that byproduct, which is hydrogen fluoride. And, these products can be, inherently toxic to us. They can be inherently toxic to the earth. They can be inert, but there could be a significant quantity of it. And so, there has been a significant push in chemistry recently to actually, not necessarily deal with it, but to come to terms with the fact that we need to, mitigate the amount of waste that we have from our reactions. And this is most notably, illustrated in industry where waste is accumulated on a significant scale. And yep, ubiquitous, found everywhere. Thank you, Lauren. And this is also encountered in our own laboratory setting where we, despite our best efforts, we still accumulate that waste in a relatively decent amount. So how do we deal with it exactly? Well, it can be burned off, it can be stored indefinitely, and it can be recycled. And unfortunately, with that first term, that actually just, makes the situation worse. If you have, a significant amount of chemical waste and you burn it off, there's the potential of making more toxic waste. And, recycling waste is only feasible if there's a small amount of chemical constituents in that waste. So it becomes, inherently necessary to, find greener chemical transformations to deal with this waste. And that actually goes into the second point that the Waterman group tries to accomplish. We try to make p-block bonds and products that may be academically or commercially relevant through greener chemical methods. Okay, so how do we do that? Well, we try to adhere to something that's called green chemical practices. And essentially what this says is that we try to mitigate waste through, preventative measures. And there's a whole, field behind this. There are 12 principles behind it. You don't need to memorize any of this. All you really need to know is that, principles 2 through 12 essentially try to accomplish principle 1. We want to prevent the waste that is accumulated in academia and industry and, lessen its impact on the earth and also lessen its impact on us. This is a bit of a cheesy, diagram, but I guess it gets the point across. So how do we do that? Well, in our own lab, we have a variety of reactions and chemical techniques that we can, try to adhere to green chemical practices. We can do something that can incorporate all atoms. That goes into principle 2, that's atom economy. And essentially what that says is that a new bond is being formed on the product side, and all atoms from our reactions are incorporated into that chemical constituent. We can lower the amount of energy that is input into a reaction by utilizing something like visible light irradiation as opposed to high temperatures and high heat. And we can also utilize renewable feedstocks such as carbon dioxide. But there's actually a far more important principle that we like to adhere to, and that's utilizing catalysts in our reactions. And I lied to you about those previous 3 reactions because in reality, all of them need a catalyst to actually form these chemical bonds. So what is a catalyst though? And this is pretty fundamental to our own work. A catalyst is something that essentially lowers the energy of activation of a chemical transformation. It starts off with some sort of reactants, X and Y, and it goes to a product side through some sort of either energy, endothermic or exothermic reaction, excuse me. And the black trace is essentially showing us what a barrier of energy of activation would be without a catalyst. It breaks that down into smaller steps and lowers the amount of energy input into a reaction. And if that's confusing, that is perfectly fine. I did not explain that well. Just think about the following analogy. Say you wanted to go on vacation somewhere. Say you're in Vermont and you wanted to go to California. Now, say that in order to get there, you just walked in scenario A. You just wanted to walk all the way from Vermont to California. The amount of energy that would go into that trip would be astronomical. You would have, food expenses, you would have shelter expenses, you would have a variety of expenses, and it would take a physical toll on you. So there is a cumulative energy input into that. Now think about it with scenario B. If instead of walking, you drove there or utilized a plane. Both of those modes of transportation significantly reduce the amount of energy that is put into you going from Vermont to California. And that's exactly what a catalyst does. It lowers the amount of energy input into a reaction. And I hope that, kind of gives an idea of what these do in their, necessary chemical transformations. So how can catalysts be divided up? Well, they can essentially be divided up into 2 specific categories. They can be divided up as a heterogeneous catalyst or a homogeneous catalyst. Heterogeneous coming from the Greek genesis of 2 words, heteros and genus, meaning other kind, and homogeneous, meaning same kind. Now, from everybody who's taken a chemistry course, what would other kind mean to you? Just take 30 seconds in the chat. What would other kind mean to you in a catalytic setting? It's okay if you're not right. I didn't really explain it. Hey, if I give you a hint, I will be giving you the answer is what I'm trying to say. So what could other kind mean in a catalytic setting? If anybody has any ideas. Nope, that's perfectly okay. You're getting somewhere on that. Multi-components, that's an interesting answer. And yes, to an extent, but I can go over that a little bit later. But essentially, in its simplistic form, a heterogeneous catalyst is just something that reacts with the reactants in a different phase. And this can be, basically boiled down into the following example. You have some sort of solid catalyst in a beaker, and you have liquid reagents. That's all a heterogeneous system is. It's a different phased system. And for those who, may drive to school, drive to work, you encounter a heterogeneous catalyst in every day. And that's a catalytic converter in a car. It takes the raw exhaust of the engine and feeds it over solid catalysts on, I forget what the support system is, and makes these gas these gases into more milder forms of, what the toxic variants would have been. So if you've been in a car, if you've driven a car, you've experienced what the benefits of utilizing a catalytic heterogeneous catalyst is, On the other hand, all that a homogeneous catalyst and its system is that everything is in the same phase. So reactants, products, catalyst, solvent, everything is in the same phase. And I've actually given a few examples down here. And one thing I forgot to tell you at the beginning of the presentation is that it's incredible to work with organometallic reagents, especially ones that have, an amount of d electrons. Is that because most of our reagents are, a wide variety of colors. I've seen everything on the rainbow. It's amazing. You've got some manganese, you've got some iron, you've got some copper. This is a dark yellow. This is like a gorgeous orange, and this is blue. So, it's really enjoyable to see these colors on, a normal basis. And that's one thing I enjoy about my job. But that's all that a homogeneous catalyst is that everything is in the same phase. So why might we use a homogeneous system versus a heterogeneous system? Well, it's a lot easier to discern what's actually going on in a homogeneous setting as opposed to a heterogeneous. And when we know what's going on, it can help us predict future reactivity. So we in the Waterman group tried to strive towards homogeneous systems as opposed to heterogeneous. So at the end of the day, all we're really trying to accomplish is trying to, discover and advance the field of catalysis to overcome the, burdens and the issues that are commonly encountered with stoichiometric transformations. We are trying to minimize the amount of waste we get out of a system. And we are also trying to, discover newer and more efficient routes to form a P-block bonds, And so that's about the halfway point with our presentation. So if anybody has any questions, I'd like to hear them. So that's a really great question. Aaron asked, why does a homogeneous catalyst make it easier to tell what's happening? And that really comes down to the fact that we don't really have, good characterization techniques to actually understand what's going on in a heterogeneous system. We have a wide variety of systems that can, ascertain what's going on with a homogeneous system. And, this is I think this is a half-century long struggle. Like we commonly employ, what was I going to say? Heterogeneous systems, but we don't really know what really goes on with that. We have a variety of hydrogenation catalysts and, other heterogeneous, systems that we just have no idea what's going on. But that question can really be answered with our characterization techniques. They can be accomplished with homogeneous systems, not so much heterogeneous. Gabby, this slide is basically summarizing why we might choose to utilize a catalytic system over a stoichiometric system. Carly, what experiments do you use for the homogeneous systems? Well, I might be touching upon that a little bit if I think I understand your question correctly, but essentially we use these homogeneous systems to, basically operate our catalysis through. I will be discussing that a little bit more, but yeah. Okay, and what are you trying to tell about what is happening? That might help explain why homogeneous is easier to tell what you are trying to see. Oh, that was Aaron's question. So Aaron is asking, what are you trying to tell about what is happening? That might help explain why homogeneous is easier to tell what you are trying to see. And I think that's more so of an answer, but that really, I think that's an answer. Yeah. It really comes down to, what can we see in these reactions? What could we characterize from them? And what, we can take from that data that we are utilizing to characterize it with. And that just really comes down to our techniques that we can characterize it as. I'm not really an expert in heterogeneous systems, but I do talk to a group that does do that sort of catalysis. So if you have any questions, I can ask them. But yeah, yes. And Brianna's question is, so a catalyst just converts substances in essence and in its simplest form? That answer is correct, yes. And so, so the previous 20 slides have basically discussed, bringing your knowledge set up to where we can discuss this actual research. And like I said in a few slides previously, our group likes to make commercially relevant products through commercially available reagents such as silanes and phosphates. And two of the key reactions that we utilize is dehydrocoupling and hydrophosphonation. Dehydrocoupling is in the name. That is just the formation of new bonds through the loss of hydrogen gas. D means loss, hydro means H2, and coupling just means the formation of new bonds. And so heterodehydrocoupling means that two different elements are being formed into one bond. In the case of silicon nitrogen, heterodehydrocoupling, that is forming silicon nitrogen bonds through the loss of H2 gas. And so why are we choosing to talk about silicon nitrogen heterodehydrocoupling? Well, at the end of the day, this very much goes into what is grad school, and you're basically given a task. You're basically given a research question to, not only discover questions about, but also to advance the field. And that's exactly what my research question is. It's forming new silicon nitrogen bonds that we could potentially use for important uses. And these have a wide variety of applications as small molecules, as polymers, and ceramics. You don't really need to know what most of these means. Essentially, in a small molecule fashion, they have a wide variety of applications in organic syntheses. As conjugated polymers, silicon nitrogen, they're called polysiloxanes. They can be utilized in OLEDs as well as other conjugated materials. And silicon nitride polymer coatings, can be utilized in high temperature settings. And this was recently employed as a coating in the space shuttle. So a wide variety of high temperature, low reactivity applications. And this really goes into the stoichiometric, facet of these reactions, is that forming SIN bonds is dominated by stoichiometric transformations, whether it be an acid metathesis or a salt metathesis that forms these bonds through the liberation of acid or a metal salt. And heterodehydrocoupling has been utilized to form silicon nitrogen bonds. However, there are only about 60 examples, so we really want to try to expand upon that field. So where do we begin exactly? Well, even in the case of catalysis and sustainability, we are always trying to find a metal that is not only abundant, but also relatively low toxicity and can be utilized in a variety of fashions. And more often than not, we are trying to avoid the utilization of these rare earth metals, ruthenium, rhodium, and palladium. These have been commonly encountered and they are highly toxic metals. So how can we overcome this? Well, we can utilize an abundant metal such as iron. And iron is important because it has been utilized in a variety of catalytic fashions, not necessarily silicon nitrogen bond formation, but other transformations. So how do we overcome that specifically? Well, we can do something that's called looking into the lit. And looking into the lit is our way of, ascertaining what has been done and how we can potentially utilize that to solve our research question. And so looking into the lit exactly, we find that, a commercially available iron dimer, affectionately called FIP dimer, has not been utilized for silicon nitrogen bond formation, but has been utilized in silicon oxygen bond formation and boron nitrogen bond formation. So we essentially have half of our elements from both of these reactions. So potentially we can utilize this for that specific transformation. So under catalytic conditions specific reacting a silane with an amine in the presence of a small amount of iron under visible light irradiation, we find that we do see catalysis. And, this is another pause points, question time from the one thing that I said a little bit earlier, which one of these is a control reaction and which one of these actually contains the iron. And, this was a brief statement about how great it is to work with D-block elements. So if you missed that, that's perfectly fine. But which one of these reactions, either top or bottom, has the iron and which one doesn't? And there are a few context clues, I guess. Boom. Elias, Misha, both of you got it correct. So this really goes into that, very brief point that I made, that D-block compounds, because of those D electrons, they are colored compounds. So this top compound would be containing our iron, and the bottom one is just a control reaction. And if you look over here, you can actually see this reaction evolving H2 gas. So that's really cool to see. And so there's actually another principle. I'm not going to spend too much time on this, but from my bad recollection of high school chemistry, we did touch upon something that's called Le Chatelier's principle. And we can actually utilize this for our own chemical reactions. Just to, go over a brief definition, Le Chatelier's just describes a system's response to an external stimuli. We can essentially, use this to our benefit. We have some sort of reaction on the left. This is our initial reaction with, our liquid catalysis at the bottom and our headspace at the top that contains a mixture of H2 and nitrogen. We can freeze this in liquid nitrogen and pull a dynamic vacuum on this. And what this accomplishes is that it sucks out all of the volatile H2 and N2 and replaces that with a vacuum atmosphere. So essentially what's happening is that we are pushing the equilibrium to the product side and as we remove H2 gas. So that was a little bit of a cool, chemical concepts kind of come to life sort of deal. But what do we see from this actual catalysis? And what I forgot to mention was you don't really need to know what mole percent means. That just means a fraction of iron is being utilized to catalyze this reaction. So what do we see from this? Gabby, what's your question? Looks like your hand is up.
So what is it? What does any of this stuff on the screen mean? And or were you about to say that? I don't know if I'm really understanding all of this. Much of this.
No, that's perfectly fine. Basically, without getting into too much detail, this stuff is basically trying to tell us that we are accomplishing our certain chemical transformations with, a certain D-block element. And that's, it's really okay if you don't understand it. A lot of this is taught in undergrad, high school levels. Some of this is even taught in grad courses. So it's perfectly okay if you haven't, if you don't understand a lot of this. But just to get back on track, it looks like I have 15 minutes left. So I'm just going to try to go through some of this. Is that not working? Yep. And so we actually see our research question, come to life. We actually see success in this word. And I apologize for not saying this earlier. LED specifically means light emitting diode. So this is essentially just a light bulb that you get from either Lowe's or Home Depot, and you shine it on the reaction to get that catalysis. The letters stand for chemicals and elements. Carly, not in this case. That is actually my fault. I didn't discern what LED meant. So it's just a light bulb that's being shown on the chemical reaction. And so we do see this, our hypothesis and our research question, come to life. We see the successful coupling of silanes and amines to form these SiN-containing materials. And just to briefly segue, we actually saw this as a competent SiO heterodehydrocoupling catalyst, specifically making SiO bonds from the reaction between alcohols and silanes. And this can really be rationalized with, the thermodynamic sink that is silicon-oxygen bonds. They are extremely strong. They're actually one of the most strongest chemical bonds there is. So that kind of, makes sense for our reasons. And so, one thing that we did find from this study was that not enough of our iron catalyst was actually activating during catalysis. The way you can really think about this without getting into too much detail into the mechanism is that, if you hurt yourself, if you go to a doctor's office, you want to get medical help. When you're in the doctor's office, that's the active form of this catalysis. However, more often than not, you spend most of your time in the waiting room, probably most of your time in the waiting room. That's exactly what happens in this type of catalysis. We have too much of our inactive form, which is the waiting room, and not enough of our active form. So how can we overcome this? Well, we can do something that is called catalyst derivatization, or develop it further to improve upon catalysis. The way we can potentially do this is installing different groups on it. And, I'm not going to go into the synthetic detail too much, mainly because it didn't work. And this is, something you will commonly encounter in research settings, is that, there's a lot of failure to be involved in this, despite the amount of work that goes into it. And this was also encountered in trying to, utilize different compounds for this catalysis, specifically finding stuff in the lit that is not only, structurally similar, but also chemically similar to our successful dehydrocoupling catalyst, is what we found that, none of these worked for our purposes. So unfortunately, this iron improving upon iron catalysis was not feasible. And so, Aaron, I will get to your question, but I just want to wrap this up a little bit further, is that, we can either go back into the lit and potentially improve upon this with a different compound, or we can take a step back and try a different element. And lo and behold, we actually find an example from our own group where we utilize, a lanthanum catalyst in heterodehydrocoupling of silicon nitrogen bonds. And this actually turned out to be a really efficient catalyst compared to our own iron catalyst. And there are a variety of reasons why this might be superior to our iron catalyst. D-electron count gives rise to a unique type of reactivity that I'm not going to go into. It has multiple active sites, and it has a lot of routes for derivatization. And, one thing we do lose is that since it has D0 electron counts, we do see it become white, as opposed to, pretty colors that we see with iron, manganese, and copper, which is a bit unfortunate, but whatever. And, this might seem a little bit counterintuitive to our previous slide, where we want to improve upon, the issues that are encountered with stoichiometric chemistry. Specifically, we don't want to use rare earth metals, but in reality, lanthanum is not as rare as the ones we are trying to avoid, specifically ruthenium, rhodium, and palladium. It is not as inherently toxic and, as rare as those compounds. And finally, in comparison to our own iron catalyst, we see that it does efficiently form SiN bonds, not only significantly faster, but in higher concentrations, as opposed to our iron compound. So at the end of that battle, lanthanum wins over iron. And so where can we really take this? Well, our goal is, at this point, we have many routes to enhance reactivity through what is called catalyst derivatization, this guy here. The way we can do this is essentially, alter the electronic structure of lanthanum to either decrease electron density donation. We can install labile ligands, reactive ligands, increase active sites, and, decrease them as well. And, just to wrap this up a little bit further, I know I've kind of sped through the last few things, is that, on paper and what you will see in a synthetic setting is that it's a total synthetic plan from one starting point at lanthanum. We want to, react these with a variety of reagents, lithiated, potassiated, to get products that might have labile ligands, more reactive ligands, electron donation into iron, not iron, lanthanum, and so on and so forth. So it's a process, but this really summarizes my graduate work. And just to put everything in perspective, the goal of these last few slides was really to synthesize superior catalyst based on what we know from either the lit or from our own previous reactions to answer a research question, which is to efficiently form silicon nitride bonds. And so just to really hone in on one last point is that the purpose of this presentation was to efficiently form silicon nitrogen bonds through catalysis. And even though we do have a decent amount of work to do with not only lanthanum but also wrapping up a little bit of iron, this really goes into this improves upon what is found in stoichiometric processes, which form a variety of waste products, such as acids, bases, metal salts, stuff like that. This really goes into that one key talking point that I said at the beginning. Dehydrocoupling is an efficient green pathway to form chemical bonds through catalysis. And so I'd just like to wrap this up with some acknowledgements. Thanks to Rory, best boss I've ever worked with. Thanks to the Waterman Research Group, past and present. Big shout out to the Vermont Space Grant Consortium for funding me as a RA for these past few years. And yeah, more cats. Before we get into questions, I believe Lauren actually has a poll.
First of all, I loved all the questions that were coming in. If you do have, I know Aaron has a question hanging out there that we'll get to in a second, but if you have any questions, either get them into the chat or raise your hand. But we're going to just take a minute. I'm going to launch a poll, which you should see right now. There's 2 questions, and we really just like to get your feedback for the cafe. So the first question, on a scale of 1 to 5, 5 being excellent, rate the overall cafe today. And the second question, as you scroll down, 1 to 5, 5 being the highest, please rate new knowledge gained by attending this cafe. What did you learn from Matthew today? We'll just give everyone a moment to answer these questions, and then we'll get to the questions you have that Matthew can answer.
Yeah.
And I'm just gonna wait till I see a few more people answering. The polls are anonymous, so it does not get assigned to anybody. So, we're just looking for your honest feedback. You don't hurt anybody's feelings. All right, I'm gonna give it about 30 more seconds. I'd like to see a few more people respond if possible. And then yes, Gabby.
I'm sorry, I know I should have raised my hand, but this has to do with the poll. I can't submit my first answer to get to the second question.
Oh, it's the same. So just scroll down. You can't submit until you do both questions. Do you see it? Okay. All right, I'm gonna give it 10 more seconds, and then I'm gonna close the poll, and then we'll get to Aaron's question.
Yeah.
All right, I'm gonna close the poll. Thank you all for doing that. And Aaron's question for you was, what is the format of the reactions? It looks like A plus B gets the product and byproduct with a catalyst above and below the arrow, and then whatever gets discarded in the reaction on the very bottom. So reaction descriptions, do they have a consistent format?
Yes and no. I kind of segued a lot of stuff. So essentially the format of these chemical reactions is just the left side are the reagents, the right side are our products. And, the top of the arrow is either catalysts or, certain specific reaction conditions. And at the bottom, it's usually something that just comes out of the reaction. In this case, H2. I will say it does significantly, depend on the field. This is consistent with organometallic chemistry, organic chemistry, whole different story. So it's consistent with our field, not so much different fields. if that gets
Great.
to your question.
So Eric is asking, how does catalyst relate to green chemistry?
So if we go back to, I think, nope, almost got it. So if we go back to our principles of green chemistry, you know, this touches upon principle 9, which is the incorporation of catalysts. So not only do they lower the energy of activation for these chemical transformations, they also really don't produce waste. I guess you could argue that hydrogen gas is waste in its own right, but it has actually been utilized through renewable processes for these reactions. So, you know, I guess it's really, you know, dependent on that, but we don't really see hydrogen gas as a waste product since we can use it for other purposes. Carly S, what does mole percent stand for? I think that's 35. So that's just the concentration of iron relative to one reagent. So, you know, say you have 1 gram of phenylsilane, well, our silane in solution, 6 mole percent would basically equate to, I think, 6 milligrams. So it's basically a fraction of one of our reagents is what it's trying to tell you. Gabby, I see your hand raised.
I'm not sure I have any more specific questions, but I just want to say thank you. And I in the poll, I didn't mark that I had learned much very high, but that's because I didn't understand a lot of it, so I don't count that as learning.
That's okay.
But you know, but thank you.
Yeah, no problem.
And thanks for answering my questions.
Yeah, no problem. All right, Aaron, where does energy come from that the catalyst is reducing the need for it? Is it just in the sense of higher efficiency of production? Yes. So say we wanted to, you know, in an industrial setting, that's sort of what our goals are aimed towards. We want to reduce the amount of stoichiometric processes that form waste and replace those with catalytic processes. We, you know, overcome that by utilizing these chemical reagents. And, you know, the efficiency of the reaction largely depends on how well our catalyst runs. Our iron catalyst from this presentation, you know, doesn't really work well for a variety of substrates, but our lanthanum does. And that's inherent to, you know, the d electron count and a variety of other substituents around lanthanum, if that answers your question.
Well, we are at 8 o'clock right now. If anybody has a final question, we can sneak it in. Otherwise, let's all just thank Matthew for sharing his work, showing us, you know, what high-level chemistry looks like. And oh, I'm sorry, Elias has jumped in with a question. Has your group worked with metal organic frameworks at all?
That's a great question, and the answer is a flat-out no, because that goes into heterogeneous catalysts. I will say the group right next to us does work in that sense. So if you're interested, you know, reach out to Laura and I could probably put you in contact with them. But the unfortunate answer is no, we don't work with metal MOFs.
Carly asks, do you work with NASA?
I am funded through a consortium that works with NASA. So it's not necessarily the same thing as NASA, but sort of is the answer.
Great. Well, everyone, fantastic questions. I loved how engaged you all were with Matthew and his work. Thank you for joining us tonight, and hopefully we'll see you at the next cafe. It will be an in-person cafe on Saturday, November 13th, and it will be on virology, microbiology, and drugs. It's like the drugs you use to combat the various bugs. So hopefully we'll see you there. Have a good night, everyone.